Inverse of a relation. Inverse functions. The inverse of a relation is found by interchanging the x coordinates and the y coordinates of the ordered pairs of the relation. So what we are doing is switching the x and the y. The inverse of a function is not necessarily a function. When the inverse f is itself a function, it's denoted as f to the negative 1 and read as f inverse. Remember, a relation is a function if each element in the domain has a unique element in the range. We can use a vertical line test to help us determine if it's a function or not. Given the graph y equals 2x plus 4, draw the inverse graph. What is the equation of the line of symmetry? So we have a graph on the left-hand side as our straight line, and I've already listed out some of the key points. The inverse mapping, you will see, changes the x and the y. So let's change each of these points. It now becomes negative 10, negative 7, negative 4, negative 4, 0, negative 2, 4, 0, and 10, 3. Graphing those, negative 10, negative 7 is going to be down here. Negative 4, negative 4, 0, negative 2, 4, 0, and 10, positive 3. Connecting those in a nice straight line gives us our inverse function. What is the equation of the line of symmetry? So our line of symmetry is that line that our original one could be reflected around. It turns out that that line of symmetry is actually the line y equals x. And so our blue or inverse graph is a reflection of the original one about the line y equals x. So let's look at graphing an inverse of something that's a little bit different. Consider the graph of the relation shown. Sketch the graph of the inverse relation. Okay, so let's start by sketching the graph. So to sketch the graph, we're going to start with our mapping. If we're doing an inverse function, means that the x and the y are switching places. So a list of key points. Our first one is the point negative 6, 4. Then we have negative 4, 6. 0, 6, 2 and 2, 4 and 2, and finally 6 and 0. The inverse relation is going to switch those x's and y's around, and so it's going to become 4, negative 6, 6, negative 4, 6, 0, 2, 2, 2, 4, and 0, 6. Let's graph it. 4 and 6, 6 and negative 4, 6 and 0. Something's not right. I'm going to start those plotting again. I've got something in the wrong spot. Here we go. So 4 and negative 6 is the reflection of this point. Then we have 6 and negative 4. this one, I didn't count right, should be down one more. There we go. So there's the reflection of that first piece. Then we have 6 and 0. This point is the reflection of this one on our graph. 2 and 2. 2 and 4. And 0 and 6. Let me retrace that in a different color just so we can see that inverse a little bit better. And so hopefully you can see that this is a reflection in y equals x, which would be this line here. Everything has been flipped over top of that. Part B asks us to state the domain and the range of the original and its inverse. So let's do it this way. Let's go original and inverse. And let's start with the domain and then the range. So the domain of our original function is from -6 to 6. And the range of our original function is 0 to 4. In our inverse, what we've done is switch the x and the y's. So our domain is now 0, 4. And the range will be -6, 6. Part C asks us to determine whether the relation and its inverse are functions. So if we look at the red graph, if it is a function, means that I can use a vertical line test, and that nowhere will it touch that graph more than once. And it doesn't, so that means that our original one is a function. However, if we look at our blue graph, our inverse graph, there's 2 spots there where if I draw a vertical line that it would cross more than once. In this section of our graph and in this section of our graph. And so our inverse is not a function. We can do something called a horizontal line test. The horizontal line test is a test performed on the original function to determine if its inverse is a function. So let's go back and look for a minute. Our original function is the red graph. If I draw a horizontal line through that red graph, it cuts in more than one spot, and so therefore I know that my inverse graph will not be a function. When the inverse of a function is not a function, it may be possible to restrict the domain to obtain an inverse function for a portion of the original. So let's look at another example. For the graph, draw the inverse. And how should the domain of the original graph be restricted so the inverse is a function? So step 1 is drawing that inverse. Again, the mapping for an inverse exchanges the x and the y values. So key points for this graph are the points -10 and 2, -5, -3, and 0, 2. When we take the inverse of those, we end up with 2 and -10, -3, -5, and 2, 0. Graphing 2, -10, -3, -5, 2, 0. And so here is our inverse. I know that the inverse is not a function because if I draw a horizontal line through the original, it cuts in 2 spots. So that tells me that the inverse is not a function. But if we're asked how we could restrict the domain of the original one, so what part of the graph when we graph the inverse would make it a function? And the answer is that we can either restrict it to this half of our original function or this half of our original function. So we can restrict the domain in two ways. Remember that we're restricting the domain of the original to either be -10 to -5 or from -5 to 0. If we only had half of that graph, both the graph and the inverse would be functions. Consider the function f of x equals x squared minus 2. Graph the function f of x. Is the inverse of f of x a function? All right, so let's start by graphing f of x. The base function for f of x equals x squared minus 2 is x squared. Remember that that is a function that we know the graph of, and so we can quickly either make a table of values or a sketch that this is what it would look like. Okay. So we end up with y equals x squared in blue. But the function that we want is actually f of x equals x squared minus 2. And so we want to take that whole graph and we need to move it. That -2 is outside of the function, so it's going to affect the y values. And so what it's going to do is it's going to shift each of those points down 2. You can make your key points and do your mapping, or because it's only one thing, we may be able to go straight to our graph and move each of those points down 2. So I put my key points in here, 1, 1, 2, and 4. There's 2 and 4 is there. So there's my key points. If I move each of those key points down 2, I end up with this being the graph of f of x. So my key points are now the points -2 and 2, -1, -1, 0, -2, 1, -1, and 2, 2. For graphing the inverse of this means that I want to switch each of those x's and y's. So we end up with 2, -2, -1, -1, -2, 0, -1, 1, and 2, 2. Let's graph that inverse. 2 and -2. -1, -1. That's not the right spot. Let's undo that. -1, -1. There we are. -2 and 0. -1 and 1. I'm going to clean that up a little bit. I apologize. Let's make that. There we are. -1 and 1. And 2, +2. And so our inverse function becomes a graph like this. So in part A for our original function, is the inverse of our red graph a function? No, it's not, because if I do a horizontal line test on the red graph, it will cut more than once. Then we've graphed the inverse on the same set of coordinates. And part C says, how could we restrict the domain of the original so that the inverse of f of x would be a function. And again, if we had 1/2 of that parabola, then the inverse would be a function. So we need half the parabola. So our domain could either be, and there's no end point, so it's going to go all the way to -infinity, and up to 0 is the midpoint of that parabola, or from 0 up to +infinity. Last example of the day says algebraically determine the equation of the inverse of each function. Verify graphically that the relations are inverses of each other. So let's start with part A. Part A says f of x equals 3x plus 6. For doing inverses means that we're switching the x and the y. Well, f of x is really just our y coordinate. So I can change our equation to be y equals 3x plus 6. When I do the inverse, I need to switch the x and the y values. So we're going to do the same thing when we write the equation of the inverse. Means that it's now going to become x equals 3y plus 6. Usually we don't leave an equation in the form of x equals, so we're going to do some rearranging to get the y value by itself. So subtract 6 from both sides, gives me x minus 6 equals 3y. Divide both sides by 3, and we end up with our equation being y equals x minus 6 all over 3. The second example is a quadratic example, so we're starting with f of x equals x squared minus 4. As an equation, I can write it as y equals x squared minus 4. When we write the inverse, we switch the x and the y variables around, so it's x equals y squared minus 4. Again, we want to solve for y. So this is our inverse here, and this is our inverse here. Solving for y, we're going to add 4 to both sides. We end up with x plus 4 equals y squared. To get rid of the square, we need to take the square root of both sides. Because we're adding that square root sign in, remember that it can be a positive or negative value. And so the equation of our inverse is y equals plus or minus the square root of x plus 4. The question asks us to verify it graphically that the relations are inverses of each other. So you could graph both of those and show that the two equations, or that the two are actually a reflection in the line y equals x.